Hello, my name is Samar Haddo, and this is a very short talk about our paper, Space-Time GNNs. And this work is a collaboration with Carlos Canet-Solis and Alejandro Ribeiro. We have encountered data supported in graphs in applications like social media and knowledge graphs, among many others. And GNNs have achieved a huge success in learning representations from these data. However, node attributes in all of these applications are usually considered fixed or slowly changing over time. On the other hand, GNNs fall short when node attributes vary so rapidly in applications like multi-agent systems. That's because they come with two challenges. First, data is distributed among these agents and is susceptible to delays before reaching the neighbors. And since the data changes very rapidly, it means that the nodes make their predictions based on outdated information. Second, we expect that the underlying graphs and sampling rates of the signals are different between training and execution due to the highly dynamic settings of the problem. Therefore, the model should be stable to perturbations in the underlying structures. And therefore, in our paper, we aim to address these two challenges. So our objective is first to design a new convolutional layer that respects time delays in receiving the data. And second, to ensure that this new architecture is stable to perturbations when transferred from one setting to another. And in order to achieve this, we need to take one step backward to find a general definition of convolutions. And let's start with this diffusion equation. It pretty much resembles a heat equation where the rate of temperature change of a body is proportional to the difference between its own temperature and the surroundings. And in our case, the temperature is replaced with any signal x, and the difference in the signals is measured using the Laplacian operator calligraphic L. Well, the solution of this differential equation is a diffused signal at time t, which is simply the initial signal x multiplied by e to the power minus t calligraphic L. But why could this be of any interest? Well, because we can define convolutions as the weighted sum of these diffused signal as shown in this equation. And here the weights h of t is the coefficient that we aim to learn. But of course, as you might have guessed, we can't learn an infinite number of coefficients. So we need to discretize the diffusion process by replacing the integral with a summation over a finite number of parameters hk. And by that, we reach a general and learnable form of convolutions. And if we need to restore the traditional time convolutions, we simply replace calligraphic L with a time differential operator. And using Taylor series of this exponential function, we can confirm that this is equivalent to the traditional time convolutions in just one line proof. And for graph convolutions, well, calligraphic L is just replaced with a graph Laplacian or adjacency. And this is roughly the graph convolution in literature, but instead of using the graph Laplacian directly, we use its exponential. So returning back to our problems, it's obvious that we need both time and space diffusion, which means that we replace calligraphic L with a linear composition of the graph Laplacian with the time differential operator. So the signals get shifted in time and they aggregated over the graph. In other words, the embedding of one node depends on the aggregated information of its neighbors traveled from the past. So we ensure that the GNN won't see any present data from the neighbors during training and will learn to make predictions from outdated information, which solves our first challenge. Now, space-time GNNs are just a cascade of these convolutional filters followed by nonlinearities. And we need to note that it's both permutation and translation equivariant. The question now is whether this architecture is stable to perturbations, which represents changes in the underlying graphs and sampling rates. So our goal is to measure distance between the network output before and after adding joint graph and time perturbations. So first, we create a perturbed graph S by adding relative error CE and ES to the original graph S. And since our model is tolerant to permutations, we consider a permutation version of S hat. On the other hand, we perform time warping in order to compress parts of the timeline and stretch others using a function z of tau. And therefore, the time differential operator is scaled by factor 1 plus z prime of tau. And as you can see in the figure, sampling the perturbed wave accounts for sampling acceleration or deceleration throughout the original one. creating divisions in the sampling rate. And under the above models and some regularity conditions on the convolutional filters and nonlinearities, it's time to introduce our main theorem. So let's assume that the perturbation size is at most epsilon. Then the difference between the output of the trained network before and after the perturbation is bounded by a linear factor that is linear in the perturbation size epsilon up to some constant. And this constant depends on the misalignment delta between the eigenvectors of S and E, the number of layers L, and the graph size N. This implies that we can transfer learned networks between different graphs and sampling rates as long as they are epsilon close to each other. And you can find all the proofs of this theorem in our paper. In order to verify our theorem, we trained the space-time GNN to let a swarm of moving agents to learn consensus on their velocities. And the figure on the left shows that the error in the output varies linearly with the size of perturbation in the graph and time domains, which matches our theoretical results. And on the right, we tested the network on graphs and sampling rates that are different from training, and we got an error that is lower than the benchmark of this problem, which verifies that the space-time GNNs handle our two challenges successfully. And by that, I conclude my presentation. So thank you for watching, and you are welcome to visit us in our poster session at ICLR for more information. Thank you.